Hi everyone, Geography Instructor Anne Saxe here, and in this video I'd like to try to undercomplicate the adiabatic processes, as I do find this concept to be one of the more challenging for students to understand because it's something that we can't necessarily see or feel. And contrary, though, to the diagram that you see here, where you might think, oh no, we're going to have to do a bunch of complicated formulas, I actually do want to try to simplify this topic. So let's see if we can't work through this together. What are adiabatic processes? They have to do with air temperature changes. They're caused by expansion or compression, not by heat transfer to or from the outside environment. So if you think about something like the latent heat of condensation that we've previously discussed, that might ring a bell for you, where it's not about a heat transfer, but about expansion or compression, or expansion in the case of the latent heat of condensation. What happens in the adiabatic processes? Large air masses above the surface cool to the dew point temperature, and that causes the air to expand as those masses rise. For the purposes of precipitation, we're very interested in adiabatic cooling, as it's the only prominent mechanism for cloud development and rain production. So this is how air masses reach the dew point, which is vital if we want to see clouds and precipitation, or if we expect to see them, rather. And that will help us then understand more severe forms of weather that might be associated with storms. And we have two adiabatic rates that we can use, or that we will see in nature. The first is the dry adiabatic rate. And we know that in the troposphere, temperature decreases with increasing elevation. And this does happen as air rises at a standard rate. So for air that's rising, the temperature will steadily decrease by a rate of 10 degrees Celsius per 1,000 meters. Or if you want to think of it in Fahrenheit, it's 5.5 degrees per 1,000 feet. For this video, we'll just be keeping with Celsius. Then you have the saturated adiabatic rate, where cooling, or I should say, yes, the rate of cooling is going to slow because of condensation and that release of latent heat. So you still have cooling occurring as the air continues to rise, but the cooling slows, and it can depend on a number of factors, the rate, but the average rate of cooling at the saturated adiabatic lapse rate is 6 degrees Celsius per 1,000 meters. I can't remember if I said meters for the dry rate, but the dry rate was 10 degrees Celsius per 1,000 meters, and the saturated rate is 6 degrees Celsius per 1,000 meters. And you'll notice here that you would switch rates once you reach the lifting condensation level. What's that all about? What happens is, as air rises in the troposphere, the temperature continues to drop until it reaches the condensation level. And you will not see water vapor condense or turn into liquid form until it reaches a lifting condensation level. As this air rises, you see it's occurring at the dry adiabatic rate, assuming the sea level temperature is 30 degrees Celsius. We rise 1,000 meters, the air rises 1,000 meters, and the new temperature is 20 degrees Celsius, a drop of 10 degrees. If we increase our elevation another 1,000 meters, our temperature drops again by 10 degrees Celsius to 10 degrees Celsius. In this particular example, the lifting condensation level, which could also be referred to as the point at which 100% relative humidity is reached, or the dew point temperature. That is where condensation begins and clouds will form. And again, up until that point, you are using the dry adiabatic rate of 10 degrees Celsius per 1,000 meters. However, once you get to the lifting condensation level, you're going to switch to that. It may vary, but most likely it'll be just about 6 degrees Celsius per 1,000 meters. So now we've gone from 10 degrees Celsius minus 6 degrees Celsius to 4 degrees Celsius at 3,000 meters. We subtract 6 degrees Celsius again till we're at negative 2 degrees Celsius at the 4,000 meter elevation. The reverse will happen when air descends. So as air descends, it's going to sink and warm and compress. And this we'll switch back again. So see here in this example, we've used our dry adiabatic rate. We were at 25 degrees Celsius. We dropped 10 degrees to 15 degrees. We dropped another 10 degrees to be at 5 degrees Celsius. And then we see that that's where clouds form, and that's the lifting condensation level. So now we need to switch to our saturated adiabatic rate. Minus 6 gives us negative 1 degree Celsius. Minus 6 again gives us negative 7 degrees Celsius. But now that the air is going to compress and descend, we're going to see warming. So we switch back again to our dry adiabatic rate of 10 degrees Celsius per 1,000 meters. So here we were at negative 7, we add 10 to get to 3 degrees Celsius. We add another 10 for the next 1,000 meters we descend, and we're at 13 degrees Celsius, 23 degrees Celsius, 33 degrees Celsius. What we want to ask ourselves is, why is, just because the air is warming, why is the air no longer saturated? And as air warms, its water vapor capacity increases. So therefore, the relative humidity decreases. And this side of the, if it's in the case of air rising over a mountain and your orographic precipitation, we get to the leeward side, the side where air is descending and warming, and we see it's dry. The windward side, where air is rising and cooling, reducing its water vapor capacity, will be where you would see more lush vegetation and just a wetter climate in general. So this leeward side, once we get to the bottom, we see that the temperature here is actually warmer than it is on the windward side. And that's because of this process of air descending at the dry adiabatic rate. And this side of the mountain would be what we call the rain shadow. Let's have us all give it a try and see if it makes sense, because in the past I have included questions like this on exams and students seem to really struggle. I've given you the answer to the first temperature calculation at 1,000 meters. So I'm using my dry adiabatic rate of 10 degrees per 1,000 meters. I was at sea level, I was at 30 degrees Celsius. My temperature drops 10 degrees as I go up to 1,000 meters. So I subtract 10, and my new temperature is 20 degrees Celsius. Now I'm going to increase my elevation by another 1,000 meters to 2,000 meters. Be careful here. You see that this is the lifting condensation level But up to this point, it's still been dry. So I'm still going to use the dry rate for my answer here. What should that be? If you said I'm going to subtract 10 for the dry rate and get 10 degrees Celsius, you're correct. Good job. But now we are going to switch to our saturated rate. Because we've reached the lifting condensation level, latent heat is being released and it slows the rate of cooling. So as I go from 2,000 meters to 3,000 meters, I'm going to drop the temperature by 6 degrees. So if I was at 10 degrees here, minus 6, what should my new temperature be? 4 degrees Celsius. Very good. And then I increase my elevation another 1,000 feet. It doesn't say here, but I'm at 4,000 meters and I'm still using the saturated rate. So I subtract 6 from the 4 degrees Celsius. What will my new temperature be? -2. But now the air is going to descend and warm. And I'm going to switch back to the dry rate. So I had -2 degrees Celsius. I decreased my elevation by 1,000 meters. I need to not subtract because now it's getting warmer. I'm going to add 10 degrees. So I should have 8 degrees Celsius. I'm going to add another 10. Everything from this point on is going to be the dry rate. From 3,000 meters to 2,000 meters, I'm going to add another 10. 18, 28, and 38 degrees Celsius. You'll notice again here that the leeward side of the mountain, the sea level temperature is significantly higher than the sea level temperature over on the windward side. And what does this mean for us in the real world? I love to show this to students because now it starts to make sense, at least partially, how the climate of North America has come to be. And if you remember from our wind belts, we learned that these winds are coming in the mid-latitudes from the west, and they're picking up all this moisture off the Pacific Ocean. They're then being forced to rise along these extensive mountains that we have in the west, and then that air descends and warms, giving us the very large rain shadow, what we see as our desert southwest in the United States. So hopefully that brings everything all together for you, and this concept of the adiabatic processes makes more sense. Thank you for watching, and I'll see you next time.